Hello, I'm Carl Dietrich. I'm a partner with SDRS Wireless, and I also work at Virginia Tech. Over the next few minutes, we will learn a few rules for calculating with decibels. We will also learn to convert some common ratios or absolute units to and from decibels, as well as how to deal with other ratios and quantities, and do all of this with as little math as we can, so that you can make quick calculations and estimates using decibels, even without a calculator. We can't quite do this with no math at all, but we'll mostly be using arithmetic and a few easy to remember rules and numbers. Time permitting, in another video, we can take an in-depth look at the mathematical basis for decibels and the rules for calculating with them. For now, though, we'll keep things as simple as we can. We'll be back in about 10 seconds to get started. Hope to see you soon. Please see the video description for a full list of disclaimers, including the ones here, plus a timeline and helpful resources and links. Please support the channel by using our affiliate links. Welcome back to our adventure in decibels, minus most of the math. First, decibels are a special way of representing ratios, such as the ratio of two power levels. Decibels are based on a nonlinear mathematical function, the logarithm. For this video, we will avoid using the logarithm function directly and stick to simpler math such as addition, subtraction, multiplication, division, and exponentiation, or raising a number to a power, which is just repeated multiplication of the number by itself. We will also memorize a few helpful rules and numbers. Decibels are commonly used in acoustics and audio engineering to measure and make calculations that involve sound levels. We will use decibels in wireless and RF engineering because the ratios involved, such as the ratio of the power of a radio signal received by a spacecraft to the power of the same signal when it is first transmitted from a ground station on the Earth, can be very small. In the same communication link example, the ratio of the effective radiated signal power transmitted in the direction of a spacecraft by the transmitting antenna to the signal at the input of the transmitting antenna can be a very large ratio. These ratios can be smaller than a millionth or larger than a million, actually much smaller or larger. And numbers like that are cumbersome to use in calculations. In the extreme cases, it can be difficult to even imagine such small or large ratios because we can't easily see them in our everyday experience. However, decibels let us represent these very small and very large ratios using more manageable and familiar positive and negative numbers. Typically, these numbers are well within the range from negative 300 to positive 300. Enough about why we use decibels. Let's learn a few helpful numbers and basic rules that we can use to start working with decibels. Here are some common ratios expressed in dB. A ratio of 1 to 1, or 1, converts exactly to 0 dB. A ratio of 10 to 1, or 10, converts exactly to 10 dB. Another ratio of interest is 2 to 1, or 2, and that converts to 3.01 dB, which is very close to 3 dB. A ratio of 1 to 2, or 1/2, corresponds to negative 3.01 dB, or approximately negative 3 dB. The next one is a little more difficult to remember, but a ratio of 3 to 1 converts to 4.8 dB, and a ratio of 1 to 3 converts to negative 4.8 dB. We only need to remember a few rules for calculations using decibels. For calculations that use decibels to represent ratios or to represent absolute values, Addition of the decibel values replaces multiplication of the ratios or absolute values. Also, when we use decibels, subtraction replaces division. And from that rule, we can see that multiplying a decibel value by a number, which is just adding the decibel value to itself multiple times, corresponds to raising the original ratio or absolute quantity number to a power, which is really just multiplying that number by itself multiple times. There are just a few more things to remember when it is time to convert a dB value to a ratio or to an absolute quantity. First, 1 dB corresponds to a ratio of 1.2589, or very close to 1.26. And without losing very much accuracy, we can approximate this further as 1.25. If we aren't using a calculator, it'll probably be easier to work with fractions than decimal numbers, so we can further approximate the number 1.26 as 1.25 or 5/4. And if we're subtracting 1 dB from a ratio or absolute quantity that's expressed in dB, that's equivalent to multiplying the corresponding ratio or absolute quantity by 4/5. Now, using these approximations does introduce an error. The error is less than 1%, and as you add or subtract more decibels, the error does increase. However, we'll see that it is usually not necessary to add more than a few decibels or subtract more than a few decibels. Now it's time to look at a few examples. In our first example, we're going to convert a ratio of 4:1 or 4 to dB. We recall that 4 can be expressed as 2 times 2, and that in decibels, a ratio or factor of 2 is expressed as 3 decibels. Also, when working in decibels, instead of multiplying two values as we would with ratios or absolute quantities, we add the two together. So we'll add another 3 dB, which is the other 2 converted to decibels, and this is equal to 6 decibels. In the second example, we're going to convert a ratio of 5:1 or 5 to dB. To do this, we note that 5 is equal to 10 divided by 2. Now we already know that 10 as a ratio or an absolute quantity is also 10 when expressed in decibels. And we know that 2 is 3 dB, as we saw earlier and in the previous example. And we also know that when we're working in decibels, instead of dividing one value by another, we subtract the second value from the first value. So that's how we use subtraction instead of division when we're working with decibels. And that gives us a value of 7 dB, or 7 decibels. So in addition to the numbers that we've already memorized, we now know that 4 can be expressed as approximately 6 dB, and 5 can be expressed as approximately 7 dB. In our third example, we're going to convert a ratio of 8 to 1, or 8, to decibels. And in this case, we know that 8 is equal to 2 times 2 times 2. And that can also be written as 2 to the third power, because 2 is multiplied by itself 3 times. So 2 multiplications, but 3 factors, each equal to 2. In decibels, this is, again, 2 can be represented by 3 dB. So we have 3 dB, 3 dB, and 3 dB, and we replace multiplication with addition. So we can see that this is 9 decibels. And another way we could have written this is as 3 dB, and then instead of raising the number to a power as we do with ratios or absolute quantities such as watts, for example, we will multiply the dB value by this exponent. And so that becomes 3 times 3 dB, and that's also equal to 9 dB. And as we would expect, we see that this number is between our previous ratios of 5 to 1 and 10 dB. And of course this makes sense because 5 is less than 8, but 8 is less than 10. Now we're going to use knowledge that we've used in these examples and the other items that we've memorized to build a table of decibel values for additional common ratios. Here is that table where we have the ratios 1 to 1 or 0 dB, and 2 to 1 or 3 dB, as well as 3 to 1 or 4.8 dB, and 10 to 1 or 10 dB from the original numbers that we memorized. Then we have 4 to 1 and 5 to 1, corresponding to about 6 dB and 7 dB from the examples. In a similar way, we can calculate the decibel equivalents for 6 to 1, 8 to 1 we've already done, and 9 to 1, and if we want to go beyond 10, we can look at, for example, 20 to 1, 30 to 1, 100 to 1, 1,000 to 1, and you can do this for any ratio of two integer numbers by using the knowledge that we already have of decibels. However, 7 is a prime number, and it's one that we haven't memorized, so we have to make an approximation, and we do that by noting that 7 is halfway between 6 and 8, so we estimate that the dB value is also halfway between the corresponding values for 6 and 8. Now that's not exactly right, but we find that in this case it's a reasonable approximation. So even though decibels, which are based on logarithms, are nonlinear, and these numbers in the ratios are linear and evenly spaced, we're able to make this approximation for two closely spaced values, and the actual value is closer to 8.45 dB, but that is not a very large error and would not have a large effect on any calculations that use it. So based on what we've already covered, just a few memorized numbers and rules, we were able to build this table. We used a similar approach to build this table for negative dB values that correspond to ratios that are less than 1 to 1. Now we're going to look at a wireless communications example. And in this example, a signal in a radio transmitter passes through an amplifier that has a power gain of 5,000. That is, the power of the signal at the output of the amplifier will be 5,000 times the power of the signal at the input of the amplifier. We also know that the signal at the input of the amplifier is 126 milliwatts, and that a milliwatt is 1,000th of 1 watt. We could multiply the input signal power by the amplifier gain to get the output signal power in watts or kilowatts. However, that might be difficult to do without using a calculator, spreadsheet, pencil and paper, etc. So let's assume that we have converted the amplifier gain to decibels. A power gain of 5,000 converts to approximately 37 decibels, as shown here. Also, the input power of 126 milliwatts is approximately 21 dBm, which is the ratio of 126 milliwatts to a reference level of 1 milliwatt converted to decibels. Now the output power of the amplifier can be calculated as P out equals P in plus G, or the gain of the amplifier, and that is 21 dBm plus 37 dB, and the output power then expressed in dBm, or dB relative to 1 milliwatt, is 58 dBm. That part was easy, but we might need to convert the output power back to units such as watts or milliwatts. In this case, we need to use another rule based on the first one and on the fact that 10 dB is equal to a ratio of 10 to 1. In this case, every time we add 10 dB, we are multiplying by 10. Based on this and on the tables that we generated, the output power is greater than 50 dBm, which is 10 to the 5th milliwatts, or 100 watts. And we also know that the output power is at 58 dBm is less than 60 dBm, and that is 10 to the 6th milliwatts, or 1,000 watts. So we know that the output power is between 100 watts and 1,000 watts, and we can be sure that it's closer to 1,000 watts. To get closer to the exact answer, while still keeping things simple enough to avoid using a calculator, we can say that 58 dBm equals 60 dBm minus 2 dB, so that's approximately 1,000 watts times 4/5 times 4/5, and that is approximately 1,000 times 16/25, or 16,000 divided by 25. And it's relatively straightforward to calculate that that is 640 watts. The actual answer is closer to 631 watts, and that's about a 1.4% error. The error in dB is also very small, at approximately 0.006 dB. To summarize, based on just a few memorized numbers and rules, we were able to generate a table of decibel equivalents of common ratios. Further, we were able to perform a very simple yet practical wireless engineering calculation with minimal math and produce an answer very close to what could be achieved using a scientific calculator with a logarithm function. Thanks for your time. Please hit like and subscribe and support the channel by using our affiliate link if you plan to buy a featured item. We also provide consulting services and referrals.